All right, guys, gals, it is 8 a.m. and we're no longer take attendance as a university, so we're skipping that process. Let's go ahead and dive in and talk about hair follicles. Or we can wait. You know, I don't have to teach. If you want to talk, that's cool. All right, let's talk about new material. So, we left off on hair. We talked about parts of the hair. There were three main regions of the hair during a cross-sectional slice. We also have different characteristics of our hair follicles. And these different characteristics of our hair follicles include texture and color. When we think of texture, this is going to be directly linked to the cross-sectional shape of the hair. Sometimes those hairs can be straight, round, or wavy. This is a good example of blended inheritance for those of you who like Mendelian genetics. Last Tuesday, I briefly mentioned how there was those disulfide bonds in the hair that could be broken and then reformed based on pH fluctuations. That's the chemistry of a perm. We also have color, and when we think of the color of a hair, that's going to be related directly to its pigmentation. In particular, we have eumelanin, true melanin, so that's going to be the really dark brown or dark black pigmentation. We'll have a lot of eumelanin. Phenomelanin is that pigment that has the reddest coloration to it. So if somebody's, a ginger, a redhead, they're going to have a lot of phenomelanin in their hair, but not a lot of eumelanin, because that eumelanin will mask the presence of the phenomelanin. If somebody is blonde, they have very low amounts of phenomelanin and or eumelanin. Somebody who's a strawberry blonde has slightly elevated phenomelanin and almost no eumelanin. And then we have gray and white. And when you go gray or go white, you lose all pigmentation, or nearly all pigmentation. And instead of the medulla being fully filled in, the medulla becomes an empty space. And a key difference between people with white hair and people with gray hair is that people with that white hair are going to have a completely hollow medulla, and if you have gray hair, the medulla is going to be filled with little air bubbles instead. So the appearance of the arrangement of the air spaces within the medulla can influence white versus gray. Both, though, don't have any pigmentation. So here's some cross-sectional views just to help you visualize those differences, with the the eumelanin being in high concentrations in dark hair, redheads having high concentrations of phenomelanin, blondes having low concentrations of both, and then gray or white having none of both. So let's have a review question. I'll give you about 30 seconds. We no longer are keeping track of this stuff for attendance purposes or participation purposes per university policy. So I'm not as concerned about giving you time to click in. So make sure you read the question. We are going to mix and match our hairs. Rearrange them to the hair color with the most eumelanin first, and the hair with the lowest levels of eumelanin at the end. All right, 5, 4, 3, 2, 1. Let's go ahead and look at the answer. So there's some low-hanging fruit. Obviously, black hair has the most eumelanin. Gray hair or white hair has the least eumelanin. The one that really took the most critical thinking was brown hair, because that wasn't on the previous slide. So you had to think to yourself, okay, now they're not quite as dark as blackheads, but they're not quite as light as a blonde. So they need to be somewhere in between. So brown hair has the second highest concentration of eumelanin. When we're looking at red hair, it's typically going to have more eumelanin than blonde hair. Blonde hair is characterized by an almost complete lack or an incredibly small concentration of that eumelanin, and then white hair is at the end with no eumelanin at all. So, what do we use our hairs for? Well, for the most part, our hairs don't do that much anymore, particularly at the trunk and our limbs. Those little tiny hairs are so small that they're pretty much non-functional. I'd mentioned that guy that I knew that was super duper hairy. Every once in a while you'll find somebody that has enough body hair that it makes a difference to help keep them warm. But for the most part, for most of us, it's vestigial. Or another way to say it is we don't currently know the functions of those hairs. Some people will make the argument that those hairs serve the purpose of letting us know when parasites are crawling on our skin. I have a lot of memories of feeling wood ticks crawl up the side of my legs after walking and going on a hike. When we think of the hair on our scalp, that hair is pretty functional. Our scalp hair helps us to retain heat. And if you've ever had the experience of being clean-shaven and bald, and I'm not talking about a buzz cut, I mean taking a razor blade and scraping it down to the skin, it's cold. I did that once, and I remember it was the middle of summer, and I just decided, what the heck, I want to be a skinhead. And I ended up wearing a beanie hat for the next couple of weeks because my head was so cold, even though it was in the middle of the summer. When we think of pubic hair and axillary hair, that's a way to signify that you're post-pubescent, you are sexually mature and capable of reproduction. Also, those axillary and pubic hairs are also going to help transmit sexual scents. Some people find the smell of someone's natural musk to be very attractive, but not that many people that I know. Yeah, I won't go any more into that. When we think of guard hairs, those big nose hairs in your nostrils, and it seems like for whatever reason, old dudes, their nose hairs just get enormous. There's a special name for those. They're called vibrissae. And I always will remember this story from when I was younger. My mom told me that if a bee ever landed on me, I just needed to hold still, and it would leave me alone. So, of course, my older brother convinced me to throw rocks into a beehive. The bees started chasing me, and they landed on me, and I held perfectly still. And then they started to crawl up my face, up my nostrils, and got stuck in my vibrissae and stung me on the inside of my nostrils, or external nares. Thanks, Brian. When we think of our eyebrows and eyelashes, they do more than just nonverbal communication. They also help to direct sweat and keep water out of our eyes. In particular, eyebrows do a great job of channeling sweat from your sweaty forehead away from your optic regions. Eyelashes help to keep dust particles out of your eyes. And there's kind of some give and take. You want some eyelashes to keep dust out, but if your eyelashes are too long, a lot of times when they get wet, they help to concentrate water and liquids near the eye. So, you want not too long, not too short. There's a happy median for the eyelashes. Let's talk about nails. So, when we think of fingernails and toenails, the nails, they're made of a lot of keratin. These structures are hard, and they serve a very important purpose. They help to protect the sensitive parts of our body. Our phalanges, or fingers and toes, oftentimes are going to have things crush them or pinch them or try to pierce them, and our fingernails will help to prevent that from happening, or our toenails. So they provide some counterforce for us to help give us some protection. They also are going to help us with grooming and picking things apart. You can think of pulling stuff off your body. There's a reason why Dr. Pimple Popper has several million subscribers on YouTube. It's just deeply embedded in us to pick at our bodies with our fingernails. It's just weird psychology of being a human being. And when we think of just other manipulations, our fingernails are great for just interacting with the external environment. As we look at our fingernails, the hard part, the part that most people think about, is called the nail plate. And as we look at that nail plate, there's three regions of it. We have the free edge, which sticks out. We have the main body, and then there's the part that's covered up. That part that's covered up is referred to as the nail root. So we have the free edge, the body, and the root, the three main parts of our nail plate. In lab, we had a mid-sagittally sliced finger that is representative of the lower half of the screen. So this diagram from the screen hopefully looks familiar to those of you who took the time to look at the demo slide within lab. Let's move on to glands. There are two kinds of sweat glands. The technical or old school name for a sweat gland is a sudoriferous gland. And of those two kinds of sweat glands, we have apocrine sweat glands and merocrine sweat glands. And these glands are located all over our bodies. So when we think of the apocrine sweat glands, those apocrine sweat glands are, generally speaking, referred to as the stinky ones. They're the ones that become activated at puberty, and they're going to be concentrated in the axillary anogenital region, so armpits and groin for those sweat glands. There are lower concentrations of those sweat glands around the areola, particularly in individuals that have well-developed breasts. They'll have slightly larger concentrations of apocrine sweat glands within the areola, or individuals that have lots of facial hair will also have a mild increase in apocrine sweat gland concentration near that well-developed facial hair. As we look at our apocrine sweat glands, they are going to have ducts that lead to nearby hair follicles. So while they aren't going to be associated with every single hair follicle like a sebaceous gland is, most of these apocrine sweat glands will be near a hair follicle. In terms of what they produce, they have kind of a milky white sweat that's being produced. When we think of the eccrine sweat glands, the ones that are the most common in our bodies, they produce a clear serous or watery fluid that serves for thermoregulation purposes. These apocrine sweat glands primarily are believed to be responsible for secreting hair pheromones, or chemical molecules that signal sexual availability to other organisms within the species or other individuals within the same species. And that's where, people talk about their natural musk smelling good. Every once in a while, though, you can have too much of a good thing. Maybe a little musk is good, but if you have gone too long without showering, you go from smelling kind of good to having BO, body odor. The technical term for body odor is bromhidorous, which is when you have so many secretions from these apocrine sweat glands that they promote the buildup of bacteria on the surface of your skin, and then those bacteria start to release the hydrogen sulfide that smells so bad. We also have merocrine sweat glands, also known as eccrine sweat glands. And when we look at these glands, they are very common. We have incredibly high concentrations of merocrine sweat glands on our head. Think of the thermal regulation. When you get kind of nervous or anxious or you're mildly overheating, a lot of times we get sweaty temples or a sweaty forehead or sweaty palms or sweaty feet. So our scalp, our palms, and our feet, or particularly the plantar region of our feet, will have really, really high concentrations of these sweat glands. In terms of the composition of the secretion, it's mostly water, overwhelmingly water. But it's also going to contain dissolved electrolytes. It's also going to contain uric acid. And there's a secondary function of these eccrine sweat glands. Primary function is thermoregulation. A secondary function is going to be setting up the acid mantle I talked about on Tuesday. That acid mantle is part of our defense system. Our skin, the epidermis of our skin, is so salty and mildly acidic that most bacteria and microorganisms can't actually grow on the surface of our skin. Our merocrine sweat glands, in terms of the histology, sometimes will be a stratified cuboidal, sometimes are a simple cuboidal. For those of you who had me in lab, I describe them as the sprinkle donut because, to me, they just look like a donut when you have that transverse slice through the duct. And the nuclei represent the sprinkles. We also have some myoepithelial cells. So let's break apart the words here to make it a little bit more approachable. Myo is a root word we have not talked about yet in this class. Myo means muscle. Myo meaning muscle. There's 3 root words in A and P that all mean muscle. Myo is one of them. So we have a muscular cell within this epithelial layer or epithelial tissue. So these myoepithelial cells are going to be activated by our body. They have nervous activation or innervation. Once activated, they start to squeeze these sudoriferous glands, these sweat glands, and they'll squeeze the secretions out of them. So this is one of the ways that when you're nervous, even though if you're not overheating, you can still start to have sweaty palms, sweaty feet, just because of high-strung nerves. Because those high-strung nerves will activate those myoepithelial cells. Now, as we look at sweat as a whole, it starts out as a filtrate of blood plasma. And when we say filtrate of blood plasma, that's a nice way of saying that we removed liquid from the bloodstream, and we removed most of the big chunks from that liquid in the bloodstream. The biggest pieces that float around within the blood plasma are proteins. And our sweat will start out protein-free. However, really tiny things like sodium chloride, potassium chloride, calcium carbonate, there'll be small amounts of dissolved electrolytes within this blood plasma. Sodium chloride being one of the most notable. Most of these dissolved salts are going to be reabsorbed immediately back into the skin. However, not all of them are, and then they can build up on the surface. That gives us the acid mantle. It also makes you kind of salty if you've ever licked somebody who is really sweaty. In terms of how we get rid of drugs, a lot of times we can have drug metabolites excreted with our sweat. This is the basis of a lot of drug testing. In addition to being excreted with our sweat, these drug metabolites can also be excreted with the keratinocytes of our nails and our hair. And can remain a part of our body for a very long period of time. In terms of the composition of sweat, it's overwhelmingly water, it's acidic, and inhibits bacterial growth. We've already talked about that acid mantle. In terms of how much water we lose about 500 mils, about a half a kilo of water a day just by doing nothing, just by sitting there. That's called insensible perspiration. So I remember when I was cutting weight for wrestling, I could bank on losing 1/10 of a pound an hour just by doing nothing through that insensible perspiration, just by not drinking or eating. I would lose that much water weight. However, if you want to increase the amount of sweat that you're producing, you can either have a psychological stimulus. More commonly, though, we'll have a thermal stimulus, so you start to overheat. And when you start sweating so much that it makes you get wet, the technical name for that is diaphoresis. As we look at that diaphoresis, you can lose, and that's actually kind of a conservative number, 1 liter per hour. I've seen individuals lose up to 3 liters an hour when they're aggressively pursuing diaphoresis. That's not recommended, though. It's pretty tough to do that. Let's talk about sebaceous glands. In terms of our sebaceous glands, they secrete sebum. Sebum is commonly referred to as oil in common English, and in common English we'll refer to the sebaceous glands as the oil glands. But the technical name is sebum because they don't actually secrete oil. They secrete oil, proteins, and carbohydrates all mixed together. So the sebum is mostly going to be lipids. It's overwhelmingly lipids, but we'll have antimicrobial proteins and small amounts of carbohydrates. The sebum serves a very important purpose. It keeps our skin and hair lubricated. So we're nearly done with winter. Thank goodness. And a lot of you this time of year, or the last couple of months, have probably had chapped lips. And I remember thinking to myself just a couple weeks ago, why is it that licking your lips makes your lips dry out? Why does adding water to your lips dry your lips out? It seems kind of counterintuitive. And my wife looked at me and said, come on, Bob, you remove the oil from your lips. Don't you teach A&P? You should know this. And I was like, oh, yeah, that makes perfect sense. So the reason licking your lips gives you chapped lips isn't necessarily that the water dries out your lips. It's that this process of licking your lips removes the sebum from your lips. You remove the natural moisturizers, and then you get the dried out lips. In particular, there's one kind of lipid, lanolin, that's in very high concentrations within our sebum. And different organisms, different mammals have different concentrations of lanolin within their sebum. Sheep are notorious for having sky-high concentrations of lanolin present in their sebum. And the reason sheep in particular produce so much lanolin is because of the wool. Not the fur, but the wool that they have and the waterproofing of their wool. We also have Ceruminous Glands, also known as earwax glands. So, of course we have a technical name for that. We can't just call it an earwax gland. Our Ceruminous glands are a form of an apocrine gland. They're one of the multiple kinds of apocrine glands within our body. In particular, though, they are going to secrete crumin. The technical name for crumin is earwax. If you've ever seen someone getting treated for impacted crumin, that's a nice way of saying that they just have a lot of earwax built up in their ears. And, depending on where you go, sometimes getting treated for that impacted crumin is very cost-effective. There's a cash-only clinic here in Eau Claire that charges $15 to remove extra earwax. Last fall, my wife had a physical with Mayo, and during the physical, they did the squirt bottle, cleaned out her ear, and then billed us $300 to squirt water in her ear and remove the crumin. So it pays to shop around, class, especially if it's just earwax. So what's our crumin do for us? What does our earwax do for us? In particular, that crumin helps to keep the tympanic membrane, the eardrum, pliable. Our eardrum needs to be very flexible so that it can take mechanical vibrations from the ear and then transmit those mechanical vibrations into physical movement of the three small bones of the middle ear. We also are going to waterproof our ear. There are antimicrobial proteins within the crumin, and we have more vibrissae, more guard hairs present in our ears as well. And this will typically keep larger things like bees or spiders or small bugs from entering your auditory canal. Another component of our integumentary system is the mammary glands. This is a key trait of being mammals. All of us have mammary glands. By default, we all start out as female in utero, and it's not until we have a wash of testosterone in utero that we start to have sexual differentiation, or we have those phenotypic variations starting to show up. So for males, your mammary glands are vestigial. They don't really serve a purpose. For females, the purpose of mammary gland is to provide nutrient sustenance to newborn children, and they are only going to be activated during pregnancy, typically late pregnancy. So a problem that some women have that give birth prematurely is that they haven't been pregnant long enough to activate their mammary glands. And then during the process of giving birth, there's a very potent hormonal cocktail that triggers lactation immediately after birth. As we look at these secretions, they are very rich. And when I say rich, they have a lot of fat in them. These secretions, by volume, depending on when the milk is harvested from the mammary gland, can have either a very high or a very moderate amount of fat within them. When I say high, I mean 20 to 30% lipids or fat. Compared to whole milk at the store, by volume or by percent, whole milk is 3% fat. So can you imagine it's like drinking cream for those infants, which is good. I know this is kind of a tangent, but newborn infants, their stomachs are about the size of a marble. So they really can't store that much in their stomachs. So what they do put in their stomachs has to have as many calories as humanly possible. So it's really a structure and function thing. The mother's breast is producing very calorie-rich milk for the child that can't store a lot of calories in the pathetically tiny stomach. let's talk about skin cancer. Skin cancer, it's just a quagmire. It's one of the most common cancer types in the United States. It's called, and I say quagmire because it's so common and there's so many variations of it. Skin cancer has been primarily linked to damage from ultraviolet radiation hitting the nuclear genome of the cells of the skin. In particular, when we have two thymines next to each other within the genome and they're hit by ultraviolet radiation, those two thymines will be chemically altered and no longer be thymines at all. It introduces a frame shift mutation where the frame of reference shifts two nucleotides for every mutation caused by ultraviolet radiation. And, you have a couple mutations. It's not going to be that big of a deal. But over time, these mutations build up, they accumulate, and eventually we get to the point where we have cells that no longer have their self-destruction mechanism in place. That autolysis mechanism that kills off precancerous cells starts to malfunction. And now, instead of the cells self-destructing when they're precancerous, they instead don't. And instead of killing themselves off, they just keep reproducing and reproducing. And eventually, the precursor of that is those moles and freckles that we start to develop. And those are precancerous. So they aren't necessarily bad for you, but those typically are going to represent regions where melanocytes have abnormal reproduction. And that's why you have dark patches appearing on your skin. And that's why doctors will typically tell you to watch moles and freckles, because you can think of those as precursors to skin cancer. But eventually, over time, the mutations keep building up, and eventually it goes from non-malignant to malignant, which is another way of saying that it's not spreading to actively spreading throughout the body. Thankfully, though, skin cancer is really easy to find. It's on the surface of your body, so you can see it almost immediately when it starts happening. Another nice thing about skin cancer is that it's pretty easy to treat. Most people are pretty okay with having a chunk of their skin cut off. I mean, it's not that traumatic of a surgery. My father-in-law is an old farmer, and he never wears sunscreen. He's been, for 70 years, he's getting sunburned multiple times a summer. When he gets skin cancers, he'll just take a little knife and go and cut it off his face with a knife. He skips the doctor appointment now. So let's talk about the different kinds of skin cancers. We have basal cell, squamous cell, and malignant melanomas. So let's talk about the basal cell. Those basal cell carcinomas are the most treatable and the most common. Oftentimes, if somebody has a basal cell carcinoma, I'm thinking of my father-in-law right now, you can just take a little blade and pop it off with a knife. You bleed for a little bit, put a Band-Aid on it, you're fine. They're very, very treatable. Sometimes, instead of cutting off the knife, a lot of times they'll just use liquid nitrogen, just like freezing off a wart, and they'll remove it from you. So these aren't necessarily worth panicking over. Go to the doctor, get it taken care of. They have a very high survival rate, thankfully. They're also very common. So it's great that we have a super high survival rate associated with these. I've never heard of a basal cell carcinoma killing anybody. They're relatively benign. We don't typically have to worry about them. Squamous cell carcinomas, though, on the other hand, they're a little bit more serious. Instead of originating at the stratum basale, these cells are going to come from keratinocytes within the stratum spinosum. And as we're looking at these cells typically are going, or these kinds of carcinomas or cancers are going to be more pronounced. They grow a little bit faster than the basal cell carcinomas. Notably, they have a concave ulcer in the center. A key characteristic that differentiates them is that concave ulcer. The basal cell carcinomas are relatively flat or smooth across the surface. There's a very mild concaveness in the center, but the squamous cell carcinomas have a very pronounced concave ulcer within the center to help differentiate them. These, you need to go to the doctor to get them removed. They are big enough and they go deep enough that a lot of times you're going to want to get a couple stitches after having these things removed from your body just to help the wound heal, close the wound. If these don't get treated in a timely fashion, they can make it to the lymphatic system, and once they make it to the lymphatic system, they rapidly spread throughout the body. But they aren't terribly fatal. Every once in a while, you'll hear about somebody who passes away because of a squamous cell carcinoma. It's unusual. It's unlikely, but every once in a while it happens. And then there's the melanoma. The melanoma is the big killer. When somebody dies from skin cancer, it's almost always because they had a melanoma. So, even though it's the rarest form of skin cancer, most skin cancer deaths are from this kind of skin cancer. It's disproportionately deadly. And if we look at the melanoma, it's the root word melano refers to the cell type. Melanomas come from melanocytes within our bodies. And the melanocytes, if you think back to last Tuesday, these are cells that have many small branches. Melanocytes are already designed to travel throughout the epidermis. So when a melanocyte is functioning normally, it already is traveling throughout the skin. But now if we take a cell that's already designed to move around and make it a cancerous cell that's designed to move around, these guys spread fast. They spread very quickly. Every once in a while, they'll be three-dimensional. Usually, though, what ends up happening is that these melanomas are going to spread deep into the underlying connective tissues and skeletal muscle tissues. And to treat the melanomas, you have to, it's almost like taking a melon baller. You just have to scoop out all the flesh because they send out roots, for lack of a better term, down into the underlying tissues. And surgeons are very aggressive in cutting out excess tissue with the melanoma because if you leave one cell behind, you get a brand new melanoma growing in the scar tissue. So they err on the side of cutting out excessive tissues. In terms of people who get it, lots of men get melanomas. A disproportionate number of men compared to women get melanomas. Redheads, because let's face it, redheads get sunburned all the time. Or people that just get sunburned a lot when they're a kid. Or are predisposed to gain melanomas. Speaking of burns, there are different ways we can burn our body. We have first, second, and third degree burns. These burns on our bodies can be ranked in severity. A first degree burn is the least severe. So as you're getting burned, the first degree burn is the first one you'll develop. You can think of a first degree burn as a sunburn. It's only going to affect the epidermis. In particular, it's going to affect the stratum basale of the epidermis. Here's a picture of somebody who, they have one heck of a sunburn. You can see that tan line dramatically. Thankfully, first-degree burns or sunburns, they heal relatively quickly within a few days, ignoring the DNA damage that's been done. And then we have second-degree burns. You can define, in terms of like the key characteristic that makes a second-degree burn it's going to be blistering. Once we have the presence of blisters, we've progressed from first-degree to second-degree burns. And those second-degree burns go all the way through the epidermis and partially through the dermis. Depending on how bad the blistering is, it can heal in as little as a few days, or it may take a couple months, and maybe there will or will not be scars. It's possible, you probably had this happen or had it happen to a friend, to get second-degree burns from the sun. Maybe it's the middle of the summer and you fall asleep without any sunscreen on, something like that. Usually when we think of these second-degree burns, a lot of times they're going to be, pragmatically speaking, little kids that spill boiling water on themselves. That's a key cause of these second-degree burns. Or if they spill boiling oil on themselves, think of a deep fryer accident instead of a second-degree burn, you get a third-degree burn. And these third-degree burns are differentiated from the second-degree burns because we have tissue death. It goes all the way through the dermis, completely through the dermis, to the underlying areolar or adipose tissue of the hypodermis. Individuals that have these third-degree burns oftentimes are going to need to get skin grafts. And there's been some recent advances in skin grafting technology. Back in the mid-90s and early 2000s, you typically would take plugs of skin from somewhere else on the person's body, and then it almost looks like a cheese grater, and you just grate the skin off of their thigh and then slap it onto wherever they lost the skin on the other part of their body. And oftentimes those individuals would have kind of a fish scale scar pattern from where the burns healed. One of my good friends had a gasoline accident when he was younger, and he had those fish scales all over his arm as a result of that. And that's been the traditional way. In the late 2000s, we started using tilapia skins, of all things, as grafts. So taking fish skins and then putting them on the burn site and using fish skin as a source to trigger tissue regrowth. And then currently being reviewed by the FDA right now is what I think is super cool, a skin gun. They harvest multipotent stem cells from the skin of the patient, culture them in situ or in a test tube, in a tissue culture, and then they have a fancy squirt bottle and just spray them with the overpriced squirt bottle. And they take skin cells from another part of the body, grow them in a test tube, and then squirt them on the burn. And they regrow skin with no scars and with no noticeable burn after effects. That to me is just amazing. However, before that skin is healed, that person is going to be losing tons and tons of fluid from their bodies. So we need to focus on fluid replacement for individuals that have third-degree burns. Also, if we think of our skin is very important for thermal regulation. And if you are constantly oozing fluid out onto your body, that's like sitting around and always being soaking wet. And if you're always soaking wet, you're going to be very cold. So in addition to having dehydration issues, individuals that have third-degree burns also have hypothermia issues as well, because they're constantly losing body fluids to the surface of their skin. Let's talk about senescence. So as we age, some loss of functions of the integumentary system. The general pattern is as we age, our organ systems don't work as well. As we look at our skin, particularly in the late 40s, we start to see some big changes in our skin. Your body's changing. Your hair starts to lose its color. So you can either have gray or white hair. I'll admit I have way more white hairs than I care to admit, particularly in my goatee, which is why I started shaving again. And then we can have a thinning of the hair. The technical name for this is called alopecia. Technically it's an autoimmune disease when your hair starts thinning, and there's different ways it can manifest itself. Usually within males, you'll have the male pattern baldness. Within females, you just have widespread thinning of the hair as they age. The skin, particularly the dermis of the skin, becomes paper thin. And it all of a sudden is really easy to tear or injure an individual because their skin becomes loose, thin, and fragile. It also becomes very dry. And that dryness means that it cracks more. And the looseness of the skin also means that those capillaries within the dermis, that loose, irregular connective tissue that makes up the dermis, those capillaries are much more likely to be torn or burst. So we're going to have a lot more bruising in individuals as they age. A disease that, calling this a disease is kind of an exaggeration. We'll say a condition that develops as we age is called rosacea, and that's when superficial capillaries are going to be permanently dilated. We lose the ability to vasoconstrict these superficial capillaries. So these individuals, even if they feel cold, they still have lots of blood being sent to the surface of their body, which is typically going to be a sponsored erythemia response, something you would associate with someone that is overheating. I'll always remember my high school science teacher showed us a side-by-side photo as a class. There was a Tibetan monk who spent 80 years in a library, never seeing the sun. And then there was a cowboy, a cattle rancher from Montana who spent decades in the sun. And the Tibetan monk who never saw sunlight, he looked like he was in his 20s. His skin, he had good skin for being in his 70s. And then the cattle rancher who got nothing but blasted with sun for decades, his skin was wrinkly and leathery. He looked almost like a walking mummy or a bog mummy. His skin was so wrinkly. What we find is the more sun exposure we have, the more photoaging we have. And this is one of those things where your natural pigmentation is going to influence the outcome. So individuals that naturally have that deep black ebony skin, they naturally have lots of eumelanin in their skin. they don't have that much photoaging because they don't have that much damage from ultraviolet radiation. And then individuals who are normally super white or super fair-skinned, they're much more prone to photoaging because they're much more likely to have ultraviolet radiation damage their skin. Other things that happen as we age is that we have trouble regulating our body temperature as we lose function of our integumentary system. For those of you, I imagine we have a fair number of you that are CNAs in a nursing home or skilled nursing facility. That's why during the winter the thermostat is cranked to 80, and why in the summer the air conditioning is turned down to like 65 and they wear blankets all the time because they are starting to lose the ability to regulate their own body temperatures. And part of that is through the atrophy of the cutaneous vessels and the loss of subcutaneous fats. So as we age, particularly as we get into those advanced years, we lose a lot of the layers of our hypodermis. And one last review question. This is a click on target. Please click on what would best represent a melanoma. Judging from how quickly the results are coming in, I assume this is pretty straightforward. We'll give you another 10 seconds. 5, 4, 3, 2, 1. All right, let's check out our responses. Fantastic. Overwhelmingly, we clicked on the right thing as a class. So good job. Pat yourselves on the back. So we are done with the integumentary system. Let's move on to Chapter 7, the skeletal system. As we are looking at our skeletal system, this Chapter 7 in your lecture textbook focuses primarily on the functions of the bone. Chapter 8 is the name the bone chapter in your lecture textbook, and we're skipping that chapter. But let's talk about the bone. Hold on a second. Okay, hold that thought. Apparently I uploaded the wrong presentation. Oh, wait, I'm not doing Chapter 8, Chapter 7. Duh. Here we go. All right, so let's talk about Chapter 7 material. So as we look at the skeletal system, the root words you're going to see over and over and over again is oste or osteo, a root word that means bone. And as we look at the bones of our body, our teeth and bones are super durable. They're the hardest part to get rid of. Our skeleton, living skeleton, is very dynamic. It's constantly remodeling itself over the course of our lifetime. And as we study bone, the study of bone is oste for bone. Oh, that's right. I can't draw anymore. Give me a second. I'm in Google Slides now. Let's just use a pointer. Here we go. So oste means bone, and ology means study of. So the study of bones is osteology. So as we're looking at our skeletal system and we're forming these bones, we'll have a lot of tissue types at play. It's more than just bone tissue or osseous tissue. That's a super generic term. We have multiple kinds of bone tissue, we have multiple kinds of cartilage, and we have tendons and ligaments. The general rule of thumb is that, I just heard something squeaky in the background. The general rule of thumb is that as we're forming bones, we'll start off with cartilage. Cartilage will then turn into the bone. So that's the general pattern. Cartilage is the precursor, the forerunner of bones. As we look at ligaments and tendons, they are made of the same kind of tissue, that dense, regular connective tissue. And the difference between them is that ligaments are a bone-to-bone connection. A tendon is a bone-to-muscle connection. And then in terms of what our skeleton does for us, it does so many important things. It gives us support. It helps to hold us physically up. It protects us. If we think of the thoracic cage and the cranial vault, we have a lot of really sensitive organs that are being protected by our skeleton. Our skeleton allows movement. It serves as a point of leverage. As we contract skeletal muscles, they will leverage the bones of our body so that we can move our body. In particular, when we look at electrolyte balance, we store calcium and phosphate. Two key electrolytes are put into long-term storage in our skeleton or in our dense bone tissue. As we think of acid-base balance, that phosphate, as it's released into the bloodstream, is part of the phosphate buffering system. So it helps us to maintain homeostasis in regards to blood pH. And then finally, within our bones, we have red bone marrow, which about half of us have looked at in lab so far this week. And that red bone marrow is the site of blood production. That is where we make blood. So as we're looking at bone tissue, osseous tissue, there's lots of kinds of it. But all of these different kinds of bone tissue have a common pattern. First of all, they're hard. The extracellular matrix of bone tissue is going to be crystallized or mineralized, is another way to say it. The specific mineral at play is going to be calcium hydroxyapatite, and this calcium hydroxyapatite is going to have lots of calcium and phosphate ions within it. In terms of this process of making a bone hard, there's some verbs. We could say to mineralize is to add the calcium and the phosphorus to the extracellular matrix, or to make a bone hard. Another way to say that is to calcify a bone is to make the bone hard. And then, as we look at these bones that have been mineralized or calcified, we could think of them as a structure, because it's this thing, you can look at it, you can label parts of it, but bones have two or more tissue types working together for a common purpose. So we can categorize a bone not only as a tissue, but also as an organ. So if we think of bone as an organ, we'd have compact bone tissue. We'd have spongy bone tissue. We'd have red bone marrow, yellow bone marrow, hyaline cartilage, fibrocartilage, dense regular connective tissues. That's just 7 tissue types off the top of my head that are all involved with bones. So there's lots and lots of tissue types at play. Now we can categorize our bones. And as we're categorizing our bones, we can do it by shape, or we can do it by function. So as we focus on shape, long bones are probably the easiest to wrap your mind around. They are over twice as long as they are wide. Long bones are primarily used for locomotion and are going to be associated with the appendages or the appendicular skeleton. And as we look at a long bone, a lot of times, because they're associated with joints, they're going to have articular cartilage on the proximal and distal ends of them. Articular cartilage is just a kind of hyaline cartilage. We also could have short bones. And if you squint your eyes and kind of look at it sideways, short bones are about the same width as they have length. So they have approximately equal width and length to them. We also could have flat bones. And as we look at these flat bones, class, they are going to have a large plate associated with them. Common flat bones include the frontal, the parietal, the sternum, the scapula. They have these big plates associated with them. As we look at our flat bones, primarily they serve to protect soft organs underneath. Really, the only exception I can think of to that rule is going to be the scapula. It serves primarily as an anchor point for the muscles of the upper arm. And then we have the miscellaneous category. So, man, that bone-shaped weird category, known as irregular bones. And they just have wonky shapes associated with them. So the bones of the face are irregular bones. The bones of the vertebral column are irregular bones. I would be hard-pressed to find a bone outside of the face or vertebral column that's irregular, but if you gave me enough time, I probably could. But those are the two parts of the body that have the most irregular bones associated with them. Now, as we look at compact bone tissue, everybody's coughing in here now. That compact bone tissue, you might want to make a margin note, is also known as dense bone tissue. And this is going to be on the outer perimeter of all bones of the body. So we have this hard, protective shell on the outside of every bone of our body. And then on the inside of the bones, we have the soft stuff. The softer tissue type is called spongy bone. Sometimes it's referred to as cancellous bone. If you're looking at a really crusty old textbook, you'll hear the term trabecular bone referring to this because of the little fibers or trabeculae that make up the spongy bone tissue. Usually we find spongy bone tissue around the proximal and distal ends of long bones or within the epiphyses of long bones. And we'll also find a lot of a lot of spongy bone tissue in between the superficial and deep sides of a flat bone. So flat bones are going to be completely filled with spongy bone tissue. Long bones will typically only have that spongy bone tissue on the proximal and distal epiphyses. As we look at our skeleton, it's the densest part of our body. So our skeleton is going to have the most mass per unit volume associated with it. And because this, particularly the compact bone tissue, is so heavy, it's quite literally, it's a rock. Because it's just made of a crystallized mineral. So these compact bone tissues are so heavy that if we just had solid bones completely filled in with compact bone tissue, we would be incredibly durable and we'd be so stinking heavy that it would be hard to move our bodies. This is one of the key reasons why we have sinuses in our skull. We have a frontal, maxillary, ethmoidal, sphenoidal sinuses. Those hollow air spaces remove pounds of mass from our skull so that it's easier for us to wiggle our heads around. We don't need to have ginormous neck muscles to hold our head up. So our skeleton is overwhelmingly compact bone, and then we have a little spongy bone mixed in based on the mass or the weight. As we look at a long bone, these long bones can be really idealized into some broad regions. We can have epiphyses and diaphyses. The epiphyses is going to be the enlarged end on the proximal and distal end of a long bone. The diaphysis, I'm using the singular, diaphysis, is going to be the middle portion of the long bone. Our diaphysis is typically going to be hollowed out and will have a medullary cavity or marrow cavity within it. When we're young, those medullary cavities are filled with red bone marrow because as little kiddos, as we're increasing in body volume, making more red blood cells is a really important function in our bodies. We need to prioritize that. When we become adults, we start to replace our red bone marrow with yellow bone marrow, or we start to replace our ability to produce blood with an ability to store fat within our bones. So as we age, we go from making red blood cells in our bones to storing fat in our bones. Now, separating the diaphysis from the epiphyses, we have the epiphyseal plate, also known as the growth plate. And that epiphyseal plate, if we're still growing taller, is going to be hyaline cartilage. And this is going to be a zone of elongation. So as we're looking at that epiphyseal plate, this is where we will grow taller. On this slide, there's no hyaline, or in this figure, there's no hyaline cartilage, so we call this the epiphyseal line. The hyaline cartilage has been replaced with compact bone tissue. And because we can still see the epiphyseal line, this tells us a couple things. First of all, we're looking at an adult. This is a femur, the distal end of a femur. So we're looking at an adult. This adult has stopped growing taller, and we have a relatively young adult because we can still see the epiphyseal line. We have some longitudinally sliced femur sections in the lab. And if you looked at those already, or if you haven't looked at them yet, focus on how there's no epiphyseal line within those longitudinally sliced bones. It's just all spongy bone tissue. That tells us that's from a geriatric individual, somebody who's had enough time to remodel their skeleton over and over and over again, so they have lost that compact bone tissue. So the epiphyseal plate is where we grow taller. When we stop growing taller, it becomes the epiphyseal line. And then as we age, the epiphyseal line fades to just become more spongy bone tissue. As we look at the proximal and distal ends of our long bones, really in any freely moving joint, we're going to have articular cartilage, which is just a form of hyaline cartilage. It's hyaline cartilage on the bone itself. It serves the important purpose of reducing friction. It primarily is there to be slippery. We also have mild shock absorbing abilities with the hyaline cartilage, or excuse me, the articular cartilage, but mostly think of it as a friction reducer. We also have generic holes in our bones. These little holes that are all over our bones are called nutrient foramen. A foramen is a super generic term for bones, a hole in a bone that has blood vessels and nerves going through it. A nutrient foramen is, well, just a hole that we have nutrients delivered and waste products removed from within our bone. This is where blood vessels and nerves will enter and exit our bones. A couple nutrient foramen are super common and very notable from human to human. So, for instance, we have the mental foramen or the infraorbital foramen that we're asking you to learn in lab. But there's also going to be hundreds and hundreds of foramen that are going to be on one person that don't appear on the next person. These are typically going to be little tiny nutrient foramen that are harder to see. Just like we have lots of differences on the outside of our body, we have lots of differences on the insides of our bodies as well. Lining the marrow cavity of our long bones, we have some connective tissues known as an endosteum. And this endosteum primarily is going to function in dissolving the inner lining of, or the compact bone tissue of the marrow cavity. In other words, it's going to enlarge the marrow cavity. So as we grow larger, we'll have bone dissolving cells within the endosteum, causing the marrow cavity to expand. Around the outer margin of the bone, we're going to have another membrane wrapped around it. This membrane is known as the periosteum. And this periosteum can be shown right here, peeled back. This periosteum is going to serve as a site of tendon and ligament attachment. It also can be thought of as kind of a secondary layer of defense. When we break a bone or have damage to our bone, a lot of times we'll have bleeding associated with that. And that blood will be contained and congeal within the periosteum sheath. So if we break a bone, the periosteum helps to keep the blood from the broken bone localized around the site of the breakage. To help our periosteum attach to the compact bone tissue, we have some perforating fibers that are just going to embed themselves within the outer osteons of that compact bone tissue. We're also going to focus on the fact that on the innermost layer of the periosteum, we have a lot of bone-building cells. As our long bones grow wider, we need to add bone tissue to the outer perimeter, to the outside of the bone tissue, for that bone to grow wider. And that's going to occur within the periosteum of the long bone. As we look at our flat bones, think of the plate bones. So that frontal bone, the parietal bones, the occipital bones, sternum, scapula, those big flat bones of our bodies, or the ilium in our hips. These bones are going to have compact bone tissue around the outside, but then sandwiched in between the compact bone tissue, we're going to have a lot of spongy bone tissue. And even as adults, we're still going to have lots of red bone marrow in these parts of our body. So we still have the ability to make new blood as an adult, just not as much as when we were younger. In terms of that spongy bone in the middle of the flat bone, it's sometimes referred to as a diplobe, and that's going to do more than just store red bone marrow. It gives us mild shock-absorbing abilities within our flat bones. Maybe you've seen the new Trek bicycle helmets that came out last fall, but the newest models of bicycle helmets that are on the market now, instead of having pads on the inside of the helmet, they have a honeycomb on the inside of the helmet. It looks a lot like they took spongy bone tissue and just made it bigger and then put it on the inside of a helmet to add another layer of shock absorption. You also don't get as much helmet hair with them as well. It's kind of nice. So let's talk about the cells of our bones. Oste is a root word meaning bone. Genic is a root word meaning create or to create. And the root word associated with genic is the same Latin root word used for Genesis. So if you think of that first book of the Bible in the Old Testament with the story of creation, to create is the root meaning of this word. So osteogenic cells are bone creating cells, or these are cells that will create other bone cells. So another way of thinking of it is it's a multipotent stem cell. It's a new variation of an adult stem cell that we haven't talked about yet. So these multipotent stem cells are going to give us the different kinds of bone cells. These osteogenic cells will form into osteoblasts. As we think of an osteoblast, osteo meaning bone, blast meaning to build. So these are the bone builders, the cells that make the bone. They're a lot like the chondroblasts that we talked about with the Chapter 5 material. So as we look at the osteoblast, it's going to excrete that extracellular matrix, those minerals into the extracellular matrix, so that it will be surrounded by that crystalline extracellular matrix, so that hard extracellular matrix. As it's surrounding itself with calcium hydroxyapatite, or the crystalline mineral that makes the bone hard, eventually it will be completely surrounded and it will transform. In terms of what stimulates the development of osteoblasts, physical activity and high calcium concentrations will stimulate osteoblast activity. So if you want to have higher bone density, you need to have some kind of resistance training, and you need to make sure you get enough calcium in your diet, calcium and vitamin D. And if you have lots of resistance training or lots of impact training, you're going to have increased bone density. My younger brother, Matt, when he was in middle school, he did martial arts for a while. And one of the things that his sensei recommended for him to do, and I made a lot of fun of him for this, was punch a tree. So I remember going outside to the backyard, and my brother Matt, he's in his pose, and he's just punching a tree repeatedly. And I thought it was the stupidest thing ever. And then he punched me, and oh my gosh, it hurt so much. I don't recommend punching trees to make your bones stronger. I would recommend things like lifting weights or having gentle resistance activity like gardening or maybe shoveling snow. You can do more than punch a tree to increase your bone density. Eventually, though, that osteoblast is going to be completely surrounded with extracellular matrix, and it's kind of built itself into a corner. It can't get out. And then it'll morph from an osteoblast into an osteocyte. And as an osteocyte, it's just a bone-maintaining cell. Osteocytes do mild maintenance of the bone. Osteocytes are going to be located in a hollow cavity within the extracellular matrix called the lacuna. So the lacuna is the space. The cell is the osteocyte. And then connecting one lacuna to another lacuna, we have itty-bitty tiny channels or canal called canaliculi. And these canaliculi are going to be filled with extensions of the osteocyte. And they serve a very important function. if we stress out our bones, and when I say stress out, I mean apply physical stress to our bones, the canal caniculi, these little tiny extensions of the osteocyte, pick up that stress, and then we have cytoplasm flow in and out of the canaliculi, or the extensions of the cell, and that's going to allow for us, the cells, to sense when we're putting physical stress or physical strain on the bones. So if we have lots of cytoplasm getting squeezed in and then squeezed back out of the canal caniculi, or of the osteocyte extensions in the canal caniculi, that's going to upregulate osteoblast activity, and then we'll have denser bones. So hopefully they don't get as stressed out anymore. So another way of looking at this is that our bones remodel. They are constantly changing shape based on our physical activity levels. There have been some really cool studies that have looked at pitchers, Major League Baseball pitchers, and their dominant arm, their pitching arm, has incredible bone density, and then their other arm has average bone density. So even on a per limb basis, we can respond differently with asymmetries. Our next cell type is the osteoclast. And we haven't talked a lot about the clasts yet. Clast is a root word that's associated with destroying or dissolving. So what's the purpose of an osteoclast? It's going to destroy and dissolve extracellular matrix. This is part of the natural remodeling process. If you're ever in a situation where you have low blood calcium, your body will immediately go to your compact bone tissue and pull calcium from your compact bone and dump it into your bloodstream. And the cell type responsible for maintaining this calcium homeostasis is the osteoclast. Osteoclasts are notable in that they are multinucleate. They're one of the few multinucleate cells in our bodies. They form when multiple osteogenic cells fuse together. So because we have multiple cells fusing together, osteoclasts are also rather large, rather enormous cells in our bodies. Let's talk about the matrix of the bone. So the matrix is the part of a tissue that is outside of a cell. And typically we have fibers and ground substances, the two parts of a matrix. Now, within bone matrix, we typically don't focus that much on the ground substance because it's solid and it's crystallized minerals, not very liquidy. So we instead are going to focus on organic and inorganic components of this special tissue, the matrix of this very unique tissue type. The organic component is overwhelmingly going to be collagen fibers. And then the inorganic component is going to be the crystallized minerals, that calcium carbonate, calcium phosphate, calcium hydroxyapatite. There's kind of a smorgasbord of minerals that make up the inorganic component of our bones. So when we look at these two things, I want you to think of one as being the flexible part and one being the stiff part. A lot of times we can think of these components of the bone kind of like rebar and concrete. So if you've ever seen a bridge or a building getting built, a lot of times you have the steel workers go in at first and they put rebar down. And rebar is pretty good at bending and flexing just a little bit. And then they surround the rebar with a bunch of stiff, brittle concrete that gives rigidity to the building's foundation. So when we think of the minerals, think of concrete. The minerals make the bone stiff and allow the bone to resist bending forces. So as we're looking at the figure on the right, that's a bone that's been soaked in vinegar overnight. It's had all of the minerals or most of the minerals removed from it. And if you try this the next time you have a chicken leg or something. Save that chicken leg and then throw it in a bowl of vinegar overnight. If you have little kids, they love this science activity. It's a really fun experiment to do with them. And then the next morning you can pull it out and you can just tie a knot with it because you've removed the mineral component from it. And to remove the organic component from the bone, you need to bake off the proteins. So to bake off the protein fibers, usually just take that bone and throw it in the oven at 450 for an hour or two, and it'll come out super brittle and capable of snapping. as we look at compact bone tissue, our compact bone tissue is going to have a lot of osteons. When we think of the osteon, that's shown right here in the lower right-hand side of our screen. That's the structural and functional unit of our compact bone tissue. And as we're looking at these osteons, they're going to be localized around a large hole called the central canal. The old school name for that is the Haversian canal. And within that central canal, we're going to have a nerve, an arteriole, and a veniole. So we're going to have blood delivery, blood removal, and nervous system control, all traveling through the central canal of the osteocyte, the osteon. And then wrapped around in layers around the osteon, around the central canal, we're going to have the lamella, which to me represent the rings of a bullseye, or maybe the tree rings if you like transversely sliced tree trunks. Connecting one central canal to the central canal next door, we have some channels that are perpendicular. Those channels which are perpendicular to the central canal are called perforating canals. So not only do we have nutrients being delivered lengthwise or longitudinally throughout the osteon, we're also going to have nutrients travel from one osteon to the osteon next door. As we look at our spongy bone tissue isn't going to necessarily be made of osteons, but is instead going to be made of little fibers called trabeculae. And this is kind of deceptive, but the hot pink part of our monitor right now, that photomicrograph, that's the bone. And then kind of the speckled maroon red portion, that's the red bone marrow. So each of these hot pink filaments is going to be a little branch or a little trabeculae of the spongy bone tissue. And then in between the trabeculae, we have the red bone marrow. So when we think of spongy bone or cancellous bone, this is a bone tissue type that is known for housing our red bone marrow. Even as adults, we'll still store red bone marrow within our spongy bone tissue, particularly within the proximal and distal epiphyses of our long bones. As we look at the spongy bone tissue, there's very, very few osteons. There's no central canals. And the osteocytes that are within this bone are going to be just closing off the marrow. So we're not going to have great nutrient delivery within the tissue itself. We're going to rely on a lot of diffusion. And as we look at the spongy bone tissue, it's a nice compromise between strength and mass. In particular, as we look at the spongy bone tissue, it allows for us to have really great structural rigidity, but not have overwhelming mass and excessive weight associated with the bone. As we expose our bones to different stresses and different forces, the spongy bone tissue will remodel and have the trabeculae reorient along the stress lines of the spongy bone tissue to maximize the strength to weight ratio. And this will be our last slide of the day. One last thing I want to emphasize while we're on this slide. As I look at this figure, I don't see an epiphyseal line or an epiphyseal plate, so I know that this femur cross-section came from an aged individual because the bone has been remodeled so much that the epiphyse is now only filled with spongy bone tissue. And that's all we have time for today.